In chapter 4, we're going to start talking about logs and exponential functions. So the first part here is really just a little bit about exponential functions before we start talking about logs, because exponential functions and logs are inverses of each other. So if we look at this first graph here, here's a picture of a graph. Here's the formula for it. That looks kind of confusing, but it's basically e to some power. So it kind of has a curve like this. It has an asymptote. But basically what you need to know is whenever we talk about an exponential growth function, we're saying that it's increasing at a rate proportional to its current value. So when you're doing word problems and you see rate proportional, that is going to be important because that indicates to you that it's an exponential growth problem. And what it really means is you're going to be using this formula that the amount is equal to the original times e raised to the RT. You might have heard of this before, the PERT formula. So the amount is equal to the principal, or the initial amount, times e raised to the rate times time. So let me go ahead and just fill it kind of in what I just said. So rate is r, t is going to be time, a is going to be your total amount, and then p is the initial amount, and e is just a number, so e is always just going to be used in this. So this is definitely something that you want to know, and you're going to use it whenever we talk about a rate proportional. And it comes from this idea right here of this function, and looking like this. So same thing with decreasing. It just means that now we're looking at a rate of a number that's less than 0. So that's how you're going to know it's decreasing. But in the end, if you see rate proportional, it means you're using that formula from up top. So then you can see the graph, the difference in exponential decay means now your function is decreasing as we move from left to right. Otherwise, it's basically the same concept. It's just one's growing, one's reducing. So let's go ahead and look at how does this relate to logs. So on the next page, we have log functions, which hopefully this is a review. But when we talk about logs, logs are inverses of exponential functions and vice versa. So what it means is you can go back and forth between the two. So when I look at this, here's a log function. So this would be y equals log base b of x is how I would read that. If I want to convert into its equivalent exponential form, the saying that I'll tell people to kind of help remember is if you drop the log, so drop the log, and I'll explain to you what it means. Drop the log, swing the base. So that's how you can convert from one form to the other. So these go back and forth. So if you think about what this is saying, drop the log, swing the base means if I drop this log, so drop the log and then you swing this base, what that's doing is the log's going away, the base is bumping y up to an exponent. So that's kind of how I think of converting from one to the other. So I'm just getting rid of the log, and the b is now becoming the base, and y is the exponent. So really what this means is logs always are really what are the exponents. So what are the exponents that you would raise this base to get x? That's kind of what it's saying. So another way to think of this is logs really equal the exponents. So instead of saying all of what I just said, meaning what would I have to raise b to, what power, what exponent do I raise b to get x? That's exactly what this is saying. Instead of saying that, we just say what's log base b of x, and that's exactly what it means. It means what's the exponent. So we're going to look at some examples converting, but these are just kind of little hints to help you remember. And then some other things to keep note of here is the natural log and the common log. So when we talk about, like if you look in a calculator, you're going to see two buttons. You're going to see a log button and you're going to see an ln. So log really means, log of x really means log base 10. We just don't always put the 10. So that just means you're looking at a base of 10. And then the natural log is represented with ln of x, but that really means base e. So this is the inverse of the function e to the x is really what it's saying. So that's kind of two things to keep note of. So let's go ahead and just practice converting. So I'm going to start over with the log first and then go back to the exponential. So just to kind of highlight that saying again, drop the log, swing the base. So if I'm trying to get this into exponential form, I'm dropping the log and I'm swinging the base. So that means it's going to be 1 over 81 is going to equal, so 3 gets raised to the negative fourth. So drop the log, swing the base. If I go here, drop the log, so swing the base. So that would mean it's going to be 100,000 equals 10 to the fifth. So again, remember what this really is saying is what power do I raise 10 to get 100,000? Because remember, log really equals the exponent. So we can continue this, and then we'll go back and fill in the others. So drop the log, swing the base. So what exponent do I raise 2/3 to get 1? It's what it's saying. So 2/3 to the 0 power equals 1. Or I could put 1 on the other side, doesn't make a difference. So again, drop the log, swing the base. So I have 8 bumps that x to an exponent equals 4. So in this case, 8 to what power equals 4? That's what it's saying. Same thing with this one. So drop the log, swing the base. So 16 is equal to x to the fourth. So what power or what base would x have to be so I could raise it to the fourth and get 16? And then if we continue, so I have the next one here is e as my base. So that means, well, actually, hold on. So these ones are I'm going to convert those back to logs. So let me skip that for a second. Let me go to this again, just continue with this process. So this actually, before I cross off my log, notice there's no base. But remember what this really means is log base 10, because that's the common log. So log base 10 of 0.1 is equal to x. So when you don't see a base, you know that it means it's 10. So now I can drop the log, swing the base. So this is really 0.1 equals 10 to the x. Next one here, same idea, drop the log, swing the base. So this is going to be x equals 4 to the negative 1/6. I'll skip that one, go on to this log. So drop the log, swing the base. So this is the easier way to convert, I think. So it's just using that saying. But really, I'm just using the formula from up top. The saying is just a little bit more helpful to remember. And then if I look at this next one, notice that there's no base. But again, remember that this really means 0.01. This ln really means log base e. So whenever you see that, you have to realize that that really is log base e. So when I drop the log and swing the base here, it's going to be e to the negative 0.01 is equal to x plus 8. So that x plus 8 all stays on the other side. So when I get to the next one, same thing. This is really log base e of 7x. So drop the log, swing the base. So it's going to be e to the fifth equals 7x. Last one. This is the same thing as saying x plus 5 equals log base e of y minus 3. So drop the log, swing the base. I need to keep this whole x plus 5 for this one because it was all on the one side. So that means it's going to be e to the x plus 5 equals y minus 3. So drop the log, swing that base. So now if I backtrack and go to all the ones I haven't done, so going from exponential form into log form, so if you just remember that your base is going to be still the base of the log, the base of the exponent, and then the exponent is always equal to the log. And then the other part is what you're taking the log of. So when I go to write log, the base is going to be 3. And remember, logs always equal the exponent, so 2 is going to go here. So it's going to be log base 3 of 9, because that's what I'm trying to find the exponent of, or how to take the base, what exponent will give me 9. So that's why you're taking log of 9. So then if we continue this, so it's going to be kind of the same idea. So log, remember that your base is going to stay the same. So the base is 6. Your log is always going to equal the exponent, and then the other piece is this number right here. So that's what you're taking the log of. So 6 raised to what power will give me 6? That's what log is saying. So when you look at these, hopefully it's making sense. 3 to what power gives me 9? 6 to what power gives me 6? That's exactly what a log means. So if I look at the next one, my base is going to be that 1/2. Remember that the exponent is always what the log is equal to, and then 16 is what you're trying to get. And then we go on to this other one. So now we have an e. So if you think about this, it's going to be log, your e is your base, your 2x is your exponent, and y is what you're taking the log of. But instead of writing this as log base e, remember I could rewrite this as ln of y equals 2x. So really either of these are true, but this is the more common way of writing it with ln instead of writing log base e. If you look at the next one, we're going to see the same thing. So we're going to have first step is our log, our base is e. Remember, it's going to equal the exponent. And a is what we're taking log of. And instead of writing this as log base e, I can replace it with ln of a equals 4x plus 3. And then the last one, same idea, because you're going to have base e. So it's going to be log base e of 20 is equal to the negative 0.3x equals the exponent. And then instead of log base e, we could rewrite this as ln of 20 equals negative 0.3x. So that's just really converting between the two different forms. So just using that formula. And then basically for the going from exponential to logs, I just kind of talk through it. But really I'm just using the formula from the previous, or from up top on this page. So let's go ahead and look at the next page, which is just more properties. So properties of logs. So properties of natural logs, you can also apply these to any like logs with the same base. So not so much for ln of e equaling 1, but log of the same base of that same base is going to equal 1. So for example, log base 4 of 4 is going to equal 1. So that's kind of why this works, because it's log base e of e will equal 1. Basically what it's saying is 4 raised to what power is going to give me 4. So same thing. E raised to what power is going to give me e. It'll always be 1. So if it's log of the same base, taking log base of the same number that you're taking log of, that'll always equal 1. And then ln of 1 is going to equal 0, because really this will be true for any base. So even if it's log base 4 of 1. Well, 4 to what power is going to give me 1? It's going to be 0. So anytime you're taking log of 1, it'll equal 0. And then this is just saying if you're, so same thing with the base. If you have log base e of e to the x, well, in order to get the log of base e to e to the x, well, what's the exponent got to be? It's got to be x. So, for example, if I had log base 4 of 4 to the x, well, 4 raised to what power is going to give me 4 to the x? Well, it's going to be x. So it's kind of all the same. ln just means these are all with considering base e. And then these properties are all true, and these are probably going to be our most helpful properties for the next examples, because these properties are true as long as you're working with the same base. So like as long as everything's in base 4 or everything's in base 3, these properties are going to be true. So what it means is log of a product is going to be equal to separating those logs into a sum. Same thing with division. So log of a quotient is going to be the same thing as splitting those up into subtraction. And then anytime that you have something raised to a power, you can bring that out as a coefficient. Now, it doesn't go the opposite way. So meaning this is not true. Log of x plus y does not equal log of x times ln of y. So see how I kind of just reverse this? This is the opposite. You can't do this. So it's always multiplication. So a single log of a product is equal to the sum of the logs of each individual part. But you can't go opposite with that. So just keep that in mind. Same thing with the division and subtraction. It has to be that way. So this is not true. Even though I put a not equals, I'm going to also write not true. So I wanted to stand out that it's definitely not true. So if we look at doing these, so the first one here, we're going to expand. So we have a product between 3 and x, so I could rewrite this as ln of 3 plus ln of x. So basically think of that as a product. I can separate it by a sum. Division, I can separate by a difference. So ln of 8x minus ln of x plus 4. If we look at the next one, we have a 6, so I'm going to use that property down below. Anytime you have an exponent, you can bring it out in front as a coefficient. So it's just going to be 6 times ln of x. So these are all equivalent just using those properties. The next one here, the first thing I see is I have, well, first of all, the 12,000 in front. So you can kind of keep that out in front in parentheses if you want. So let me just kind of show you what I mean. So I could keep that out like this and say ln of x plus ln of y to the 5th, because it's multiplication between those, so I can split those up by addition. And then I can distribute that 12,000, or I can leave it out in front. It really doesn't make a difference here. Just know that it could go either way. So then I have this. I can bring this 5 out in front though. So it's going to be 5 because now it's an exponent can become a coefficient. And then you can leave it like that, or you could distribute this. And like I said, you could have distributed it right from the beginning. It doesn't really matter. So I get 12,000 ln x, multiply those, so we get 60,000 ln y. And really, either one of these would be considered an answer for that. Doesn't really make a difference. So now the next page is going back, or the next section here is going backwards. So now that it's expanded, we're going to use those properties to condense it. So the first thing you're going to want to do is before you combine addition, you want to take care of any coefficients. So kind of like if you look here what I did, I always first split up products and quotients. I split those up into addition or subtraction. Then I dealt with the exponents. Now I'm going to do things backwards. So that means I'm going to move these coefficients up as exponents so that I can then combine sums and differences into products or quotients. So the first thing I'm going to do is take care of that exponent. And now that I have a sum, I can rewrite this as a product of the two pieces. And that's it for that one. if I look at this one, there's no coefficients, so there's no exponents. But what I'm going to do is I'm going to combine this difference first as a quotient. So ln of A over B minus ln of C. So when you run into something like this, just work left to right. Like, don't worry about which one comes first. Just go in left to right order. And then from here, now I have another difference, so I can rewrite this as another quotient. So what it's going to be, I'm going to have A over B divided by C. So that's rewritten as a single log expression. Now instead of leaving it like this, I'm going to rewrite it since it's a fraction divided by another number. I'm going to go ahead and I'm going to rewrite it as multiplication. So it's going to be, remember when you divide fractions, you keep the first one, flip, so keep, change, flip. So you're going to change the sign to multiplication. You're going to flip the bottom. So instead of C over 1, it's going to be 1 over C. So really what this is going to end up being is ln of A times A over B times C. So that's it. And remember, for these, you just go left to right and you just use those rules to simplify.